One of the people in that press conference, our space correspondent Miles O'Brien, who in the last 36 hours or so has shown his knowledge of the space program to be nothing short of extraordinary. As I said, he was in the press conference, and it is to him we go for some analysis now at the Johnson Space Center in Houston. Miles?
Anderson, right at the top of the press conference, after Ron Dittemore laid out sort of the organizational issues on how to go about going through this whole complex puzzle that is an investigation of this nature. Complex, probably a euphemism. It's hard to comprehend how they're going to put all these pieces together. But you had a sense that, first of all, this is a fairly well-run ship thus far, fairly well organized. Contrast that to the post-Challenger investigation, which to a person, everybody who was involved in that and who was around at that time described it as in disarray. Mayhem is the word. It was a difficult time. NASA was not as prepared for this. That last 5 minutes, we had some incredible detail about what happened to the orbiter Columbia in that last 5 minutes. 8:54 a.m. Eastern Time, high temperature readings in the left fuselage section of the orbiter, 60-degree spike in 5 minutes, whereas on the other side, a 15-degree spike over the same period of time. Interestingly, though, the temperature inside the cargo bay, the payload bay, normal. 8:58 a.m. over New Mexico. The elevons or ailerons, those are the control surfaces, the flaps at the tail end of the space shuttle, were compensating for a problem which was tilting the shuttle to the left. It was trying to compensate for that tilt to the left by putting in trim, in other words, moving those control surfaces in the opposite direction. This is something, in other words, it was trying to go this way, and so the computers were trying as best it could, using those flaps on the back, to try and reverse that trend. That is consistent, according to Dittemore, with the loss of a tile or rough tiles, these black tiles in the surface. Now, 8:59 a.m. over West Texas, the roll trim on that was not saturated, which means it hadn't completely reached the point where it was out of authority, couldn't do its job, but it was doing everything it could to get the vehicle back into level flight where it was going this way. So it tells you that all the failure modes were going on here. It was getting hot over here, and the orbiter was dipping in that direction. There's a lot more to go over. As you said, Anderson, very long news conference, a lot of technical detail. Someone here to help us sort it out is Norm Thagard, shuttle veteran who is now with the Florida State University. Norm, what are your thoughts? One thing that came out was an interesting little artifact, if you will, about the computer data and how much data they have in their computers here at Mission Control.
Well, Ron mentioned that after the loss of communications, the vehicle was still well under control, meaning although it had the trim in, it was well within the ability of the computers to command the flight surfaces and the reaction jets to maintain it. And then he indicated that after the loss of comm, there was another 32 seconds of data that has to be hand analyzed, basically, because it had problems. It had errors in the frames, the way they send the data down in packets, so they'll have to go in and go through and do it.
In other words, there was some sort of a stream of data coming from Columbia, apparently, but kind of a sick stream or an intermittent one, and we don't know how to interpret that is a difficult question, right?
That was my sense of it. If I'd had the ability to ask Ron to clarify, I would have asked, is that what you mean? But it sounded like he was saying there was still another 32 seconds of data coming from the vehicle after the loss of communication.
All right, a lot of time spent discussing not the end of Columbia's final mission, but the beginning of the mission. 81 or 82 seconds after launch, there was an event that has a lot of people's attention, not just in the media, but many engineers all throughout the NASA community. Let's take a look at a close-up. We've managed to blow up some tape that we get typically, engineering views, cameras of the ascent of the space shuttle. And if you take a look at that close-up there. Let's do it one more time. You see very clearly a white piece, a white flash that there you go. You see that right there. There's the circle. And then it goes out of view. But it's very clear that whatever fell off there appears to have struck the underside somewhere of the space shuttle Columbia. Norm, this is a hard thing to interpret, and we're asking us to do a lot of armchair engineering here. What do you think of that?
Well, it's white, and I've seen the white stuff come off the external tank on several missions. it is foam insulation usually. If it's ice, I think you'd worry a lot more because ice could potentially be harder, have more mass. You wouldn't really expect a foam insulation to do much damage.
All right, the ice is the issue, and we got to remind folks of what's inside that orange external tank, the coldest substance on Earth, liquid hydrogen, minus 400 degrees, along with liquid oxygen. That's the rocket fuel that powers the main engines on the space shuttle. Randy Avera, former NASA lead engineer on the shuttle program, give us a sense, if you would, of how much significance that white flash has. First of all, do you think you've isolated the moment in time that we're all talking about?
Here at the CNN Center, we've looked at two videos, the one that you've just seen, plus another angle that shows a more white, visible object passing in the area under the belly of the orbiter where the black tiles are located, and then apparently makes impact and is atomized, and as the debris or particles continue towards the flame of the solid rocket booster, they vaporize. It's important to note that NASA is doing a very important thing here very well. Back in 1986, when the orbiter Challenger was breaking up, we had photos and videos very early on showing the crew module flying through the air, and then a big bright flash where the propellants in the nose of the orbiter in front of the crew module had a big bright white flash. Well, that made us think a lot of things that took us down a wrong path. What NASA's doing very well is following the correct procedure, looking at the data, and here on this orbiter model that we have, it's in this area of this rectangular shaped door, the main landing gear wheel well door. Now, I've worked inside that wheel well before, and the whole landing gear strut and the tires and brakes retract up into here, and there are mechanical systems, electrical wiring, and hydraulic lines in here. And what NASA's describing is a spike of temperature inside this wheel well. The wheel well is part of the wing assembly. It's part of the wing structure. And that's what NASA's looking at, and what effect, if any, did this have on the performance of the ailerons. And what NASA's also describing is that the orbiter on the left side is actually being pulled, as Miles and Norm have been pointing out, to the left. And just like the inner ear in humans, the balance system in the orbiter is called the inertial measurement units for roll, pitch, and yaw rates. It senses this tug and pull, and the general purpose computers and software compensate to pull it back on trajectory for the approach to landing.
Now, Randy, one thought I have in looking at that tape, and granted, we don't have the best view here. There's some high-speed film, which we'd love to get a hold of and take a look at, which the engineers have used. But it appears that white flash that we see strikes near the nose. I don't know if you concur with that, Norm, but it's very difficult to tell where it ultimately ends up, I suppose. Randy?
Well, my direct comment on that is that what you see is not always what is the case. And the lesson learned in '86 is the optics from video is very deceiving. It's only one small piece of the large equation that NASA's trying to solve to find out all the variables, whether it was one event that caused this problem or a combination of events, and specifically, what's the difference between a malfunction and a failure. That was a very important thing back in '86, talking about solid rocket booster O-rings and steel casings. What was the failure and what was the malfunction?
Norm Thagard, what are your thoughts on what we're seeing there and whether that is striking where we hear there were problems, which is to say the left wheel well?
It's very difficult in that picture, Miles, to tell exactly where it does hit. It potentially hits back in the left underwing area, but again, that video is not very clear.
And just pick up on Randy's final point here, Norm, this sense of we got to really watch ourselves getting the blinders on here. This is important, right?
That's absolutely true, because if it is foam material, which is the most likely thing for it to be, it almost certainly didn't cause this kind of damage. It hits the windscreens on shuttle, and all it does is streak them. So if it's not breaking glass and the other, you wouldn't think it would do this kind of damage.
Randy, but having said that, going from the blinders comment to this fact, wouldn't it be an amazing coincidence if there was damage to the left wing on ascent, and it just so happened on the descent to Earth, the area of the left wing was the point of failure?
Well, there are many factors that go into this. Last night we were talking about with astronaut Story Musgrave how the way we used to describe the shuttle, a butterfly strapped to a bullet. And we showed earlier today on CNN how the glass coating on a tile is very fragile, about the thickness of your fingernail. That's that black ceramic glass coating on the black tiles. And also, we've been in orbit for 16 days. There are micrometeorites. There are a lot of factors that could play in. And all of those scenarios have to be analyzed, thought of, documented, and digested. And conclusions are far down the road.
Norm Thagard.